When we look up at the night sky, we see stars twinkling peacefully, distant and serene, but scattered throughout the cosmos are objects so extreme, so bizarre, that they challenge everything we think we know about physics and reality itself. Today, we're going on a journey to explore some of the most extraordinary phenomena in the universe, starting with an object that might be even stranger than black holes themselves. Let me ask you a question. What happens when a massive star dies? Most people know the answer. It either becomes a neutron star or collapses into a black hole. But what if there's a third possibility? What if some dying stars transform into something so peculiar that scientists are still debating whether they can even exist? These hypothetical objects are called Gravastars, and they represent one of the most fascinating ideas in modern astrophysics. The story of Gravastars begins where all extreme cosmic objects begin, with the death of a massive star. When a star many times larger than our Sun runs out of fuel, it can no longer support itself against its own crushing gravity. The core collapses in less than a second, and the outer layers come crashing down, only to rebound in a catastrophic explosion we call a supernova. This explosion is so bright it can briefly outshine an entire galaxy containing hundreds of billions of stars. Now, here's where things get interesting. In the traditional view, if the collapsing core is massive enough, it keeps collapsing forever, shrinking down to an infinitely small point called a singularity. This singularity becomes surrounded by an event horizon, the point of no return, and we call the whole structure a black hole. But singularities are problematic. They represent places where our laws of physics completely break down, where mathematical equations start spitting out infinite values and nonsensical answers. Many physicists find this deeply unsatisfying. Enter the Gravastar hypothesis, proposed in the early 2000s by physicists looking for alternatives to black holes. The name itself is a combination of gravitational vacuum star. Instead of collapsing all the way to a singularity, the Gravastar theory suggests that something remarkable happens at the core. The matter doesn't compress into an infinitely small point. Instead, it undergoes a phase transition, similar to how water can suddenly freeze into ice, or how carbon under extreme pressure becomes diamond. But this phase transition is far more exotic than anything we see in everyday life. According to the theory, the intense pressure during the collapse forces matter to transform into a form of vacuum energy. Now, vacuum energy is a genuinely strange concept that deserves explanation. In quantum physics, what we think of as empty space isn't actually empty at all. The vacuum of space is filled with quantum fields, and these fields have an inherent energy even when no particles are present. Normally, this vacuum energy is incredibly diffuse and weak, but inside a Gravastar, the collapse compresses this vacuum energy to an almost unimaginable density. Think of it this way. Imagine you have a sponge full of water. Normally, the water is spread throughout the sponge, but now imagine you could squeeze that sponge down to the size of a grain of sand while keeping all the water inside. The density of water in that tiny space would be enormous. Similarly, a Gravastar would contain vacuum energy compressed to densities that approach but never quite reach the infinite density of a black hole singularity. This compressed vacuum energy has a peculiar property. It creates a repulsive gravitational effect. Yes, you heard that right. Gravity can be repulsive under certain exotic conditions. This repulsive pressure pushes outward with tremendous force, counteracting the inward crush of gravity. The result is a standoff, a cosmic tug-of-war that reaches a stable equilibrium. But the story doesn't end with just the core. The Gravastar hypothesis proposes that this compressed vacuum core is surrounded by a shell of exotic matter. This shell is unlike any material we've ever encountered. It would need to be incredibly thin, perhaps thinner than an atom, yet simultaneously strong enough to contain the enormous energies within. The shell would be made of matter in an extreme state, possibly something called a Bose-Einstein condensate, pushed to its absolute limits. A Bose-Einstein condensate is a state of matter that occurs at temperatures close to absolute zero, where atoms lose their individual identities and behave as a single quantum entity. The shell of a Gravastar would be extraordinarily cold, perhaps only a fraction of a degree above absolute zero, making it one of the coldest objects in the universe. At the same time, it would be under such extreme tension that stretching it even slightly would require stupendous amounts of energy. So what would a Gravastar actually look like if we could observe one? From the outside, it would appear remarkably similar to a black hole. It would be perfectly black, absorbing virtually all light that falls on it. It would have an immense gravitational field that warps space and time around it. Matter falling toward it would form a bright accretion disk, spiraling inward and heating up to millions of degrees before disappearing at the surface. To a distant observer, the Gravastar would be indistinguishable from a black hole using conventional observation methods. But there's one crucial difference. A black hole has an event horizon, a mathematical boundary in space. Once you cross the event horizon, you can never escape, and you will inevitably be pulled into the singularity at the center. A Gravastar, on the other hand, has a physical surface. It's an actual shell made of matter, incredibly exotic matter, but matter nonetheless. This distinction might seem subtle, but it has profound implications. For one thing, Gravastars avoid the information paradox that has plagued black hole physics for decades. The information paradox asks a simple question: what happens to information when it falls into a black hole? According to quantum mechanics, information cannot be destroyed, but according to black hole physics, anything that crosses the event horizon is lost forever, seemingly destroying the information it contained. This contradiction has been one of the biggest unsolved problems in theoretical physics. Gravastars, lacking an event horizon and singularity, sidestep this problem entirely. Information would be encoded in the shell and the internal structure rather than being lost. Now you might be wondering, is there any evidence for Gravastars? Do they actually exist, or are they just an interesting mathematical possibility? The honest answer is that we don't know yet. No one has definitively observed a Gravastar, and it's possible they don't exist at all. But the fact that they're mathematically consistent with our laws of physics means they deserve serious consideration. The challenge is that Gravastars would look almost identical to black holes from far away. We need to find subtle differences that would allow us to distinguish between them. One promising avenue involves gravitational waves, ripples in space-time caused by the motion of massive objects. When two black holes collide and merge, they produce a characteristic pattern of gravitational waves that we can detect with instruments like LIGO and Virgo. If two Gravastars were to collide, they would produce a slightly different pattern because they have physical surfaces rather than event horizons. Specifically, the collision of Gravastars might produce what scientists call echoes in the gravitational wave signal. These echoes would be very subtle, delayed reflections of the main signal caused by waves bouncing off the physical surface. Several research groups are actively searching for these echoes in gravitational wave data. So far, the results are inconclusive. Some analyses have suggested possible hints of echoes, but the signals are at the very edge of detectability, and more data is needed to make any definitive conclusions. Even if Gravastars don't exist in nature, studying them teaches us important lessons about the extremes of physics. They show us that there might be alternatives to black holes, other ways that matter and energy can behave under extreme conditions. They remind us that our current theories, while remarkably successful, might not be the final word. And they push us to develop better observational techniques and more sophisticated theories. The Gravastar concept also connects to broader questions about the nature of space-time and quantum gravity. One of the great challenges in physics is reconciling general relativity, our theory of gravity and space-time, with quantum mechanics, our theory of the very small. These two theories are both extraordinarily successful in their own domains, but they seem fundamentally incompatible when we try to combine them. Black hole singularities are places where this incompatibility becomes acute, where both quantum effects and extreme gravity are important simultaneously. Gravastars, by avoiding singularities, might give us hints about how a more complete theory of quantum gravity would work. While we're contemplating Gravastars, let's turn our attention to an extreme object that we know definitely exists: neutron stars. These objects are only slightly less bizarre than Gravastars, and they're absolutely real. We've observed thousands of them, and they're among the most extreme environments in the known universe. Neutron stars are born in the same supernova explosions that might create black holes or Gravastars, but they form when the collapsing core isn't quite massive enough to overcome a certain threshold. Instead of collapsing completely, the matter is compressed to nuclear densities, where protons and electrons are squeezed together to form neutrons. The result is an object about 20 kilometers across, roughly the size of a city, but containing more mass than our entire Sun. Let me give you some perspective on just how dense a neutron star is. If you could take a teaspoon of neutron star material and bring it to Earth, it would weigh about 1 billion tons. That's roughly the weight of a mountain compressed into a volume smaller than a sugar cube. The gravity at the surface of a neutron star is about 200 billion times stronger than Earth's gravity. If you could somehow stand on a neutron star, you would be instantly flattened to a layer just a few atoms thick. The interior structure of a neutron star is like nothing else in the universe. At the surface, there's a thin crust made of atomic nuclei packed together in a crystalline lattice, similar to metal but far denser. Below that is a layer where atomic nuclei are so tightly packed they start to merge and form exotic shapes, like rods and plates rather than spheres. Scientists sometimes call this the nuclear pasta layer because these structures resemble different types of pasta: spaghetti, lasagna, and so on. Deeper still, we reach the outer core, where matter breaks down completely into a fluid of neutrons, protons, and electrons. The pressure here is so intense that neutrons are packed together far more tightly than in any atomic nucleus. And at the very center, in the inner core, conditions are so extreme that we're not entirely sure what happens. The matter might transform into exotic states containing strange quarks, or even form a quark-gluon plasma, similar to what existed in the first microseconds after the Big Bang. Neutron stars also have the strongest magnetic fields in the universe. Earth's magnetic field is what makes a compass needle point north and protects us from solar radiation. The magnetic field of a typical neutron star is about 1 trillion times stronger. There's a special class of neutron stars called magnetars that have fields another 1,000 times stronger still. These magnetic fields are so powerful they can distort the very atoms in the star's crust, causing starquakes when the crust suddenly cracks and rearranges itself. Many neutron stars rotate at incredible speeds. Some spin hundreds of times per second, faster than a kitchen blender. These rapidly rotating neutron stars are called pulsars because they emit beams of radiation from their magnetic poles, and as the star spins, these beams sweep across space like a lighthouse beam. If Earth happens to lie in the path of one of these beams, we see regular pulses of radio waves or other radiation. Some pulsars keep time more accurately than atomic clocks, pulsing with such regularity that astronomers have considered using them as cosmic navigation beacons for future interstellar spacecraft. The discovery of neutron stars and pulsars is itself a fascinating story. They were predicted theoretically in the 1930s, shortly after the discovery of the neutron itself. But many physicists thought they were too bizarre to actually exist in nature. Then in 1967, a graduate student named Jocelyn Bell Burnell noticed a strange repeating signal in her radio telescope data. The signal was so regular that she and her advisor initially wondered if they had detected a signal from an alien civilization. They jokingly called it LGM-1 for Little Green Men. But they soon found more of these signals and realized they had discovered a new type of astronomical object. This discovery was awarded the Nobel Prize, though controversially, Bell Burnell herself was not included as a recipient. Neutron stars are also the source of some of the most violent events in the universe. When two neutron stars orbit each other, they gradually lose energy by emitting gravitational waves, causing their orbits to decay. Eventually, they spiral into each other and collide in a catastrophic merger. This collision produces multiple spectacular phenomena simultaneously. It creates a powerful gravitational wave signal that we can detect with instruments on Earth. It produces a bright kilonova explosion powered by radioactive decay of heavy elements, and it generates intense beams of gamma rays. We've observed several of these neutron star mergers in recent years, and they're invaluable for studying extreme physics and for understanding where heavy elements like gold and platinum come from. Speaking of heavy elements, neutron star mergers are thought to be one of the primary sources of heavy elements in the universe. When neutrons are thrown off during the collision, they can rapidly attach to atomic nuclei in a process called rapid neutron capture, or the R process. This creates elements heavier than iron, including precious metals and radioactive elements like uranium. The gold in your jewelry, the platinum in catalytic converters, the iodine in your body, all of it was likely forged in neutron star collisions billions of years ago. Now let's venture into even more speculative territory. What if neutron stars aren't the final word in dense matter? What if there's an intermediate state between neutron stars and black holes? This brings us to the concept of quark stars, another hypothetical object that pushes the boundaries of extreme physics. To understand quark stars, we need to dive briefly into the structure of matter. Ordinary matter is made of atoms, which consist of electrons orbiting a nucleus. The nucleus contains protons and neutrons. But protons and neutrons aren't fundamental particles. They're made of even smaller particles called quarks, held together by particles called gluons. Under normal conditions, quarks are always confined inside protons and neutrons. You can never isolate an individual quark because the force holding them together actually gets stronger as you try to pull them apart. But what happens under the incredible pressures inside a neutron star? At some critical density, the neutrons might be squeezed so tightly that they break apart, releasing their constituent quarks. The result would be what's called quark matter, a state where quarks move freely rather than being confined to individual protons and neutrons. A star made primarily of quark matter would be a quark star. Quark stars would be even denser than neutron stars, perhaps 30 to 40% smaller for the same mass. They might have layered structures, with a neutron star crust surrounding a quark matter core, or they might be entirely quark matter. The surface gravity would be even more extreme than a neutron star, and the magnetic fields could be even stronger. One particularly intriguing possibility involves strange quark matter. Normal matter contains up quarks and down quarks. But there are other types of quarks, including the strange quark. Under extreme conditions, it's possible that matter containing strange quarks might actually be more stable than normal matter. If this is true, then strange quark matter might be the true ground state of matter, the most stable configuration possible. This hypothesis is called the strange matter hypothesis, and it has some mind-bending implications. If strange matter is truly more stable than normal matter, then any normal matter that touches it would be converted to strange matter in a runaway chain reaction. A single tiny nugget of strange matter, sometimes called a strange lay, could potentially convert an entire planet or star. This sounds like science fiction, but it's a serious theoretical possibility that physicists have considered. The good news is that even if strange matter exists, strangelets would be extremely rare, and any we encounter would likely pass right through Earth without interacting. Still, it's a fascinating and slightly unsettling idea. Some researchers have proposed that certain observed neutron stars might actually be quark stars in disguise. The differences would be subtle, mostly apparent in precise measurements of mass, radius, and cooling rates. As our observational capabilities improve, we might be able to detect these differences and confirm or rule out the existence of quark stars. Let's step back from the most extreme objects and talk about white dwarfs, the fate awaiting the vast majority of stars, including our own Sun. While not as exotic as neutron stars or Gravastars, white dwarfs are fascinating objects in their own right and represent a crucial stage in stellar evolution. When a star like our Sun exhausts the hydrogen fuel in its core, it begins to die, though not explosively like more massive stars. Instead, it swells into a red giant, expanding until it might engulf the inner planets. Eventually, the outer layers drift away, forming a beautiful planetary nebula, while the core contracts into a white dwarf. A white dwarf is roughly the size of Earth, but contains about half the Sun's mass. The matter is compressed to densities about 1 million times that of water. What keeps a white dwarf from collapsing further? The answer involves a quantum mechanical principle called electron degeneracy pressure. According to the Pauli exclusion principle, no two electrons can occupy exactly the same quantum state. When electrons are packed tightly together in a white dwarf, they're forced into higher and higher energy states simply because all the lower states are occupied. This creates a pressure that has nothing to do with temperature and everything to do with quantum mechanics. This degeneracy pressure is what supports the white dwarf against gravitational collapse. White dwarfs have no internal energy source. They're essentially cosmic embers, slowly cooling over billions of years. A newly formed white dwarf might have a surface temperature of 100,000 degrees or more, making it incredibly bright despite its small size. Over time, it cools and fades, eventually becoming a black dwarf, though the universe isn't old enough yet for any black dwarfs to exist. Some white dwarfs have an additional source of energy that makes them anything but quiet. If a white dwarf is in a binary system with another star, it can pull matter from its companion. This matter spirals onto the white dwarf, building up on its surface. Eventually, the accumulated hydrogen reaches critical temperature and pressure, igniting in a runaway thermonuclear explosion called a nova. The white dwarf itself survives this explosion, and the process can repeat multiple times over millions of years. But there's an even more dramatic possibility. If a white dwarf accumulates enough mass, either from a companion star or by merging with another white dwarf, it can approach a critical limit called the Chandrasekhar limit, about 1.4 times the mass of the Sun. Beyond this limit, electron degeneracy pressure can no longer support the star. The white dwarf collapses, triggering a runaway nuclear reaction that completely destroys the star in a Type Ia supernova. Type Ia supernovae are incredibly important in astronomy because they're remarkably consistent. They all reach roughly the same peak brightness, making them excellent standard candles for measuring cosmic distances. In fact, observations of distant Type Ia supernovae in the late 1990s led to the discovery that the expansion of the universe is accelerating, a finding that earned the Nobel Prize and introduced the concept of dark energy. We've talked about alternatives and related objects, but we can't discuss extreme physics without addressing black holes themselves, the objects that Gravastars were proposed as an alternative to. Black holes represent the ultimate endpoint of gravitational collapse, and they remain one of the most fascinating and perplexing objects in the universe. A black hole forms when matter is compressed beyond a critical point where not even quantum degeneracy pressure can resist gravity. The matter collapses to a singularity, and an event horizon forms around it. The event horizon is the defining feature of a black hole. It's the boundary where the escape velocity equals the speed of light. Once you cross the event horizon, no amount of force, no rocket, no matter how powerful, can ever bring you back out. You will inevitably fall toward the singularity. Black holes come in different sizes. Stellar mass black holes, formed from collapsed stars, typically contain between 3 and 20 times the Sun's mass. Supermassive black holes, found at the centers of galaxies, can contain millions or even billions of solar masses. There are also intermediate mass black holes, which are more mysterious and harder to detect. And theoretically, microscopic primordial black holes could have formed in the early universe, though none have been definitively detected. One of the most counterintuitive aspects of black holes involves time. As you approach a black hole, time itself slows down relative to distant observers due to gravitational time dilation. If you were to watch someone fall into a black hole from a safe distance, you would see them move slower and slower as they approach the event horizon, never quite seeming to cross it. Their light would also redshift, becoming dimmer and redder until they faded from view. But from the perspective of the person falling in, they would cross the event horizon in a finite time, noticing nothing particularly special at that moment. Only later would the increasing tidal forces, the difference in gravitational pull between their head and feet, tear them apart in a process colourfully called spaghettification. Black holes aren't completely black, at least theoretically. Stephen Hawking showed in the 1970s that quantum effects near the event horizon cause black holes to emit radiation, now called Hawking radiation. This radiation carries energy away from the black hole, causing it to slowly evaporate over time. For stellar mass black holes, this process is incredibly slow, taking far longer than the current age of the universe. But for hypothetical microscopic black holes, the evaporation could be rapid, ending in an explosive burst of radiation. The existence of Hawking radiation creates what's known as the black hole information paradox. According to quantum mechanics, information cannot be destroyed. But Hawking radiation appears to be thermal, meaning it carries no information about what fell into the black hole. So where does the information go? This paradox has driven decades of research in theoretical physics, leading to concepts like black hole complementarity and the holographic principle, which suggests that all the information about the interior of a black hole is somehow encoded on its event horizon. We've now directly imaged black holes, or more precisely, we've imaged the glowing matter surrounding them. The Event Horizon Telescope, a global network of radio telescopes, has captured images of the supermassive black holes at the centers of the Messier 87 galaxy and our own Milky Way. These images show a bright ring of light surrounding a dark shadow, the shadow being larger than the event horizon due to light-bending effects. These images are stunning confirmations of general relativity and have allowed us to test predictions about black hole behavior with unprecedented precision. Black holes also play crucial roles in galaxy evolution. Nearly every large galaxy has a supermassive black hole at its center, and the properties of the black hole correlate closely with properties of the galaxy as a whole. As matter falls into a supermassive black hole, it heats up and emits enormous amounts of energy, sometimes outshining the entire galaxy. This active galactic nucleus can generate powerful jets that shoot material out into intergalactic space at nearly the speed of light. These jets can influence star formation throughout the galaxy, creating a feedback loop between the black hole and its host galaxy. Let's zoom out from individual objects to consider the large-scale structure of the universe. When we do, we encounter two profound mysteries: dark matter and dark energy. Together, these invisible components make up about 95% of the total mass energy of the universe. Everything we can see, all the stars, planets, gas, dust, and radiation, is just 5% of the cosmic budget. Dark matter was first proposed in the 1930s when astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving far too fast. Based on the visible matter alone, the cluster shouldn't have enough gravity to hold itself together. The galaxies should have flown apart long ago. Zwicky proposed that there must be invisible matter providing additional gravitational attraction. The idea was largely ignored for decades until the 1970s, when astronomer Vera Rubin made similar observations of individual galaxies. Rubin studied the rotation curves of spiral galaxies, measuring how fast stars orbit at different distances from the galactic center. According to Newton's laws, stars farther from the center should orbit more slowly, just as outer planets in our solar system orbit more slowly than inner planets. But Rubin found that stars in the outer parts of galaxies were orbiting just as fast as stars closer to the center. The only explanation was that galaxies are embedded in large halos of invisible matter extending far beyond the visible disk. Since then, evidence for dark matter has accumulated from multiple independent sources. We see its gravitational effects on galaxy clusters, in the patterns of gravitational lensing, where light from distant objects is bent by intervening mass, and in the cosmic microwave background radiation from the early universe. All this evidence points to the same conclusion: there's about 5 times as much dark matter as ordinary matter in the universe. But what is dark matter? Despite decades of searching, we don't know. It doesn't emit, absorb, or reflect light, which is why it's dark. It doesn't seem to interact with ordinary matter except through gravity. The leading hypothesis is that dark matter consists of exotic, subatomic particles that were created in the Big Bang, but that don't interact with normal matter through the electromagnetic or strong nuclear forces. Physicists have proposed various candidates with names like WIMPs, weakly interacting massive particles, and axions. Experiments around the world are searching for these particles, but so far none have been definitively detected. There are alternative theories that try to explain the observations without invoking dark matter. These modified gravity theories suggest that our understanding of gravity might be incomplete, and that gravity behaves differently on galactic scales than we expect. The most developed of these is called MOND, for Modified Newtonian Dynamics. While MOND can explain some observations, it struggles with others, particularly the cosmic microwave background and gravitational lensing. The scientific consensus strongly favours dark matter, but the modified gravity alternatives remind us to keep an open mind. Dark energy is an even deeper mystery. In the late 1990s, 2 teams of astronomers were measuring distances to faraway supernovae to determine the universe's expansion rate. They expected to find that the expansion was slowing down due to gravitational attraction. Instead, they found the opposite. The expansion is speeding up. Something is pushing the universe apart, and we call this mysterious, something dark energy. Dark energy appears to be a property of space itself. As the universe expands, more space is created, and with it, more dark energy. This causes the expansion rate to increase over time. Dark energy currently makes up about 68% of the total energy density of the universe. with dark matter at 27% and ordinary matter at just 5%. The simplest explanation for dark energy is Einstein's cosmological constant, a term he added to his equations of general relativity to create a static universe. When it turned out the universe was expanding, Einstein called the cosmological constant his biggest blunder. But now it seems he might have been right after all, just for the wrong reasons. The cosmological constant can be interpreted as the energy density of the vacuum, the same vacuum energy we discussed in the context of Gravastars. However, when physicists try to calculate this vacuum energy from quantum field theory, they get an answer that's wrong by a factor of 10 to the power of 10 power of 120, the worst prediction in the history of physics. Other theories suggest dark energy might be a dynamic field called quintessence that changes over time, or that it might be evidence that general relativity needs modification on cosmic scales. Future observations, particularly of how dark energy has evolved over cosmic history, should help us distinguish between these possibilities. To truly understand the extreme objects we've been discussing, we need to understand where they came from. That takes us back to the beginning, to the Big Bang and the early universe. The story of cosmic origins is one of the most remarkable achievements of 20th century science, and it involves some of the most extreme conditions imaginable. The universe began about 13.8 billion years ago in an incredibly hot, dense state. In the first fraction of a second, the universe was far too hot for atoms to exist. Matter existed as a plasma of quarks, gluons, and other fundamental particles. As the universe expanded and cooled, quarks combined to form protons and neutrons in the first microsecond. It took 3 minutes for protons and neutrons to combine into the first atomic nuclei, creating mostly hydrogen and helium. But it took another 380,000 years before the universe cooled enough for electrons to combine with nuclei to form the first atoms. This moment when atoms formed, called recombination, had a dramatic effect. Before recombination, the universe was opaque because photons constantly scattered off free electrons. After recombination, photons could travel freely through space. The light from this moment has been travelling through the universe ever since, stretched by cosmic expansion into microwaves. This is the cosmic microwave background radiation, and it's one of the most important sources of information about the early universe. But there's a puzzle about the early universe that the standard Big Bang theory couldn't explain. When we look at the cosmic microwave background, we see that it has almost exactly the same temperature in all directions, varying by only about 1 part in 100,000. This seems unremarkable until you realize that regions on opposite sides of the sky have never been in contact with each other. Light from one region hasn't had time to reach the other region in the age of the universe. So how do they know to have the same temperature? How did they reach thermal equilibrium if they've never interacted? The solution to this and other puzzles is cosmic inflation, a period of exponentially rapid expansion that occurred in the first tiny fraction of a second after the Big Bang. During inflation, the universe doubled in size at least 60 times in less than a trillionth of a trillionth of a trillionth of a second. This rapid expansion took a tiny region that was in thermal equilibrium and stretched it to encompass the entire observable universe. Inflation also explains the origin of structure in the universe. Quantum fluctuations during inflation, tiny random variations in density, were stretched to cosmic scales. After inflation ended, these density variations acted as seeds for structure formation. Denser regions had slightly stronger gravity and pulled in more matter, eventually collapsing to form the first stars and galaxies. The pattern of these density variations is imprinted in the cosmic microwave background, and it matches remarkably well with what inflation predicts. The physics of inflation involves quantum field theory and general relativity in an extreme regime. The rapid expansion was driven by a hypothetical scalar field called the inflaton, which had enormous energy density. When inflation ended, the inflaton field's energy was converted into ordinary matter and radiation, reheating the universe. This process, called reheating, created all the particles that make up the universe today. We've explored the extremes of matter and space across the universe. Now let's look forward to the ultimate fate of everything. What does the distant future hold? The answer depends on the nature of dark energy and the overall geometry of the universe. If dark energy remains constant, as current evidence suggests, then the universe will continue expanding forever at an accelerating rate. Galaxies outside our local group will eventually recede from us faster than the speed of light. Not because they're moving through space faster than light, but because space itself is expanding. These galaxies will disappear beyond our cosmic horizon. Future astronomers, trillions of years from now, will only see their local group of galaxies and will have no way to know that a larger universe exists beyond. Star formation will continue for many billions of years, but eventually the universe will run out of hydrogen to fuel new stars. The last stars will be tiny red dwarfs, burning slowly for trillions of years. When even these finally die, the universe will enter the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, and black holes. These objects will slowly evaporate through quantum processes. White dwarfs will crystallize, forming giant diamonds. Protons themselves might decay, though this has never been observed and might take 10 to the power of 40 years if it happens at all. Eventually we reach the black hole era, when black holes are the dominant form of mass in the universe. But even black holes don't last forever. Through Hawking radiation, they slowly evaporate, with the rate depending on their mass. Stellar mass black holes will take about 10 to the power of 67 years to evaporate. Supermassive black holes will last far longer, up to 10 to the power of 100 years. But eventually, even they will vanish in a final burst of radiation. What remains after the last black hole evaporates? A universe of nearly infinite size and incredibly low density, containing only a thin soup of photons, neutrinos, and maybe electrons and positrons. This is the dark era, when the temperature of the universe has dropped to nearly absolute zero and nothing interesting can happen anymore. This is heat death, the ultimate state of maximum entropy. The universe doesn't end with a bang or a whimper, but with a long, cold silence. But this might not be the whole story. If dark energy is not constant, but instead grows stronger over time, we could face a different fate called the Big Rip. In this scenario, dark energy eventually becomes so powerful that it tears everything apart. First, galaxy clusters are ripped apart, then galaxies themselves. Eventually, even solar systems are disrupted and planets are torn from their orbits. Finally, stars, planets, and even atoms are shredded as space expands faster than the forces holding them together can counteract. The Big Rip would occur at a finite time in the future, perhaps 20 billion years from now, depending on the properties of dark energy. Another possibility is the Big Crunch. If there's enough matter in the universe, and if dark energy eventually weakens or reverses, gravity could eventually overcome the expansion. The universe would begin to contract, with galaxies moving toward each other instead of away. As space contracts, everything would heat up. The cosmic microwave background would shift from microwaves to infrared to visible light to ultraviolet and beyond. Eventually, everything would be compressed back into a hot, dense state similar to the Big Bang. Some theories suggest this could lead to a big bounce, where the universe cycles through repeated expansions and contractions. Current observations suggest none of these alternatives is likely. The universe appears to be flat or nearly flat, meaning it will expand forever, and dark energy shows no signs of changing. But we've been surprised before, and our understanding of dark energy is still very limited. Future observations will refine our picture of the cosmos and its ultimate destiny. We've journeyed through some of the most extreme and bizarre objects in the universe, from hypothetical Gravastars to very real neutron stars, from the mysterious dark matter that holds galaxies together to the dark energy that's tearing the universe apart. Along the way, we've encountered singularities where physics breaks down, quantum fluctuations that seed galaxies, and timescales that boggle the human mind. What strikes me most about all of this is how much we've learned and how much remains unknown. A century ago, we didn't know that other galaxies existed. We didn't know the universe was expanding. We had no idea about neutron stars, black holes, or dark energy. The progress we've made is staggering. We've gone from barely understanding stars to imaging black holes, detecting gravitational waves, and mapping the structure of the entire observable universe. Yet for every answer we find, we discover new questions. We don't know what dark matter is made of. We don't know why dark energy has the value it does. We don't know if Gravastars or Quark Stars exist. We don't know what happens at the singularity inside a black hole. We don't know if string theory or loop quantum gravity or some other approach will finally unite quantum mechanics with general relativity. We don't even know if we're asking the right questions. This is the beauty of science. It's not about having all the answers. It's about the process of discovery, the thrill of finding something unexpected, the satisfaction of solving a mystery, and the humility of realizing how much we don't know. Every generation of scientists builds on the work of previous generations, and every discovery opens new frontiers to explore. The objects we've discussed today represent the extremes of what's possible in our universe. They show us that reality is far stranger and more wonderful than we could have imagined. They remind us that the universe operates according to mathematical laws that we can understand, even when those laws lead to seemingly impossible conclusions. And they inspire us to keep looking, keep questioning, and keep pushing the boundaries of knowledge. One day, we might finally detect those faint gravitational echoes, proof that Gravastars truly exist. We may isolate the elusive particle behind dark matter. We might even forge a complete theory of quantum gravity, one that unites space, time, and energy into a single equation. Or perhaps the cosmos will throw us something entirely unanticipated, a phenomenon so alien that every textbook must be rewritten. Because that's the true nature of the universe. The moment we think we understand it, it reveals another layer. Every discovery opens a deeper question. Every answer leads to a new paradox. And somewhere out there, beyond the reach of even our most powerful telescopes, reality is playing by rules we haven't yet learned to read. So when you look at the night sky, don't just see distant suns. Imagine entire realms of physics hiding in plain sight. Black holes threading space-time into knots. Neutron stars beating like cosmic hearts hundreds of times each second. Hypothetical Gravastars, neither fully matter nor fully void, suspended in a balance that defies logic. All of it woven into a vast framework of dark matter and dark energy, invisible yet undeniable, steering the fate of galaxies. And if that's what we've discovered so far, imagine what lies beyond. What if there are objects stranger than black holes? Entities that don't destroy information, but store it. What if there are forms of matter that exist only under pressures found inside collapsing stars? What if space itself behaves differently in parts of the universe we haven't yet reached? What if time flows at different speeds in different regions, not just near gravity wells, but across entire cosmic domains. What if consciousness, the very act of observing, plays a role in the structure of reality at the deepest level? Perhaps there are cosmic structures we haven't even imagined, vast networks of invisible filaments that thread not just galaxies but realities together, like veins of a deeper multiverse. Perhaps between those filaments drift objects older than time as we measure it, relics from a pre-Big Bang epoch, carrying information about a universe that existed before our own. The signals we interpret as random noise in our detectors could be messages from these ancient structures, waiting for us to develop the sensitivity to decode them. Even our most powerful telescopes might be seeing only a fraction of what truly exists, their mirrors reflecting just a thin slice of reality's spectrum. What lies beyond could dwarf our current understanding: particles that travel backward through time, waves of space-time vibrating like music across unimaginable distances, or entire regions where the laws of physics differ slightly, enough to create forms of matter and energy we have no words for yet. As our instruments grow sharper and our theories more daring, we inch closer to glimpsing these hidden layers. Each discovery does not close a chapter, but opens a new one, revealing that the universe is not a static stage, but a living, evolving mystery whose rules are still being written. Or maybe the universe isn't just stranger than we imagine. Maybe it's stranger than we can imagine. Maybe the reason so many of our theories break down at the edges, at singularities, at the Planck scale, at the birth of the universe, is because reality is not made to be neatly compressed into human logic. Perhaps there are regions where dimensions do not behave linearly, where time branches like a river delta instead of flowing in one direction. In those domains, cause and effect might swap places. Events could loop endlessly, rewriting themselves. From our perspective, such places would look impossible, but from within, they may be perfectly consistent. There could be stars powered not by nuclear fusion, but by processes we have no name for yet, crystallized quark matter humming with unknown forces. There could be planets that never formed from rock or gas, but condensed directly from dark matter, invisible yet massive, shaping orbits without ever reflecting light. There could even be conscious structures on scales beyond. Comprehension, not individual beings, but collective intelligences formed from magnetic fields spanning light years, thinking in patterns of plasma and radiation. And what if the very void between galaxies is not empty at all, but alive with particles flickering in and out of existence so rapidly that, on average, they cancel each other, yet underneath, they obey hidden rhythms? What if dark energy, the thing pushing the universe apart, is not a passive force, but an active pressure applied from outside our space-time? What if our entire observable universe is just one expanding bubble among countless others, each governed by different physics, colliding and merging in ways that leave echoes we've mistaken for background radiation? We may soon build instruments capable of hearing those echoes. Next-generation interferometers may register ripples in reality itself, tremors from neighbouring universes bumping against ours like waves against a shore. Quantum sensors cooled near absolute zero might detect the soft background hum of virtual particles, swapping identities faster than thought. Even cosmic rays striking our atmosphere could be fragments of physics from another domain, passing through ours like sparks from a fire we have not yet seen. And when we finally detect something that truly does not fit, not a glitch, not an anomaly, but undeniable evidence of a deeper layer beneath everything, it will not be the end of science. It will be the beginning of something entirely new. And if all of this is possible, if the universe hides layers we've barely begun to uncover, then the real question isn't what exists, but how far we're willing to go to find it. Our current tools are brilliant, but primitive compared to what may come. Today, we send metal telescopes into orbit and sift through data streams. But tomorrow, we may deploy observatories woven directly into space-time. Instruments that don't just look at the universe, but participate in it. Imagine detectors stretched along the magnetic fields of entire galaxies, listening to cosmic vibrations the way a spider senses motion through its web. Imagine probes made from programmable matter, tiny swarms capable of rearranging themselves mid-flight, adapting to environments no human craft could survive. Some may dive into the event horizons of black holes to send back quantum-encoded whispers from the boundary of existence. Others may ride the cosmic background radiation itself like surfers on invisible tides. There could be spacecraft that do not travel through space in the traditional sense, but fold around it, slipping between geometric configurations the way a page can be bent to meet another. Such vessels wouldn't accelerate, they would reconfigure. Entire journeys between stars could become transitions rather than voyages. Even consciousness may one day become part of our toolkit. If the brain is a physical system obeying quantum rules, then thought itself might be refined into an instrument, trained to perceive patterns that machines cannot. Just as birds can sense magnetic fields and whales navigate with sound across oceans, perhaps humans will evolve or engineer the ability to perceive space-time curvature, gravitational noise, or probability flows directly. Not magic, biology enhanced by insight. At that point, science and perception might merge. Exploration would no longer be limited to engines and equations. It would be an act of awareness, a moment where discovery is not just measured, but experienced. And maybe, in those future moments, we'll realize that the universe was never silent or distant. It was always speaking, through gravity waves, neutrinos, polarized light, magnetic storms. And we were simply not yet fluent in its language. And so, from the faintest ripples of gravity to the deepest mysteries of dark matter, from black holes and neutron stars to the unseen architecture of space and time itself, the universe remains both our greatest teacher and our most challenging riddle. Every time we build a sharper instrument or frame a new question, the cosmos answers by expanding the horizon of what's possible. We are explorers born into a reality far larger than our senses, and for the first time in history, we have tools capable of piercing that darkness. With each experiment, each observation, each new theory, we carve out a little more clarity from the unknown. Yet the unknown always stays ahead, drawing us forward. That is not a failure of science, it is the essence of discovery. So when you look up tonight, remember, those points of light are not just stars. They're markers of something vast, ancient and ongoing. A story still being written in which you and I are living participants. The journey from wonder to knowledge isn't ending, it's accelerating. And the greatest discoveries, the ones that will redefine everything we think we know about reality, may still be waiting just beyond our reach. Keep looking up. Keep asking, keep imagining, because the universe rewards curiosity, and its next secret might be the one that changes everything. And if there's one truth the cosmos has whispered through every era, it's that we are not passive observers. We are the very medium through which the universe comes to know itself. Our questions are not interruptions to its silence, they are echoes of its own unfolding. Each spark of insight, each leap of imagination is the cosmos reflecting back at us, reminding us that awareness is woven into its fabric. The sky above is not a ceiling, it is an invitation. Galaxies drift like lanterns in the dark, carrying with them billions of stories untold. Black holes twist the laws of time into knots we are only beginning to untangle. Even the emptiness between the stars, once thought barren, hums with unseen particles, hidden energies, and possibilities we have yet to name. And perhaps that is the most extraordinary revelation, that mystery itself is not a wall, but a bridge. Every unknown is a path, every unanswered question a frontier. We stand at the shoreline of an ocean that has no end, and each new discovery pushes the horizon farther, daring us to follow. So we continue, not because we expect final answers, but because the act of seeking is what defines us. To be human is to wonder, to search, to reach beyond what is given. And in that reaching, we do more than map the stars. We map ourselves. The story of the universe is still being written, and our curiosity is the ink. And maybe one day, far in the future, we'll look back on this era the way we now look back at the first fire lit in the dark, as the moment we began to see. The telescopes we build, the detectors we launch, the questions we ask, these are our torches carried into a night so vast it could swallow imagination itself. Yet with every flicker of light we ignite, the shadows reveal not just the cosmos, but the strange fact that we belong to it. For the atoms that shape our bones were forged in stars, and the time that carries us forward is sculpted by the same forces that bend galaxies. The universe does not sit apart from us. It runs through us, as intimately as blood through a vein. And in that realization lies both humility and wonder. We are brief, but we are made of eternity. Perhaps this is why we keep searching, not only to understand black holes or dark matter, but to understand what it means to exist at all. Every cosmic mystery mirrors a human one. What is time? What is consciousness? Why is there something instead of nothing? These questions are not abstract puzzles. They are the pulse of our own awareness, beating in rhythm with the stars. And so, with each century, the line between the known and the unknown shifts. Where once the horizon was the edge of the Earth, it became the orbit of planets, then the glow of galaxies, and now the very structure of space and time. Each expansion rewrites the story of who we are. Each discovery reminds us that certainty is small, but wonder is infinite. So do not fear the unknown. Embrace it, for it is the unknown that has carried us this far, and it is the unknown that will carry us farther still. The night sky is not a void. It is a mirror. And when we look into it, we do not just see the universe. We see the next chapter of ourselves. And so, as we drift at this intersection between what we know and what still lies hidden, we have to remind ourselves of something essential. Discovery is not just about answers, it's about presence. To stand under the night sky, to look upward, to wonder at what might be beyond sight, that itself is a form of discovery. It is an act of participation in the grand unfolding of reality. The great mistake would be to think the universe is a riddle we will one day solve completely, as if all of its secrets could be stacked neatly into a final equation. Number. The cosmos is not a puzzle with a single solution. It is a living ocean of questions, and every answer we grasp only multiplies them further. When we discovered gravity, it opened the door to relativity. When we uncovered the atom, it led to the mysteries of quantum physics. Every milestone is both an ending and a beginning. That is not failure, that is growth. Think about this. The light you see tonight may have left its star millions of years before the first humans ever walked the earth. You are not just seeing light, you are seeing ancient history written in photons, crossing a gulf of time so vast our minds can barely hold it. The universe has been speaking for billions of years, scattering messages across the void, and only now have we built the eyes and ears to listen. And what does it tell us? That creation is not static, it is ongoing. Galaxies collide, stars are born, others collapse into black holes. Planets form, some perhaps fertile, some barren. The same forces that shaped us are still at work, sculpting new worlds, new possibilities, new stories. We are not living at the end of history. We are living inside its unfolding. Perhaps that is why curiosity feels so deeply human. It is not just a hobby or a luxury, it is survival. It is connection. It is the same drive that led our ancestors to light fires in caves, to cross oceans, to map the globe, and now to send telescopes beyond our solar system. We have always been seekers, and in seeking, we have always found more than we imagined. Yet in all of this searching, there is a lesson we cannot ignore. The universe does not promise comfort. The truth is not always gentle. Space is cold. Time is relentless. Stars die. Worlds burn. Even galaxies dissolve. And yet within that reality, there is beauty so staggering that it outweighs the darkness. For every collapse, there is creation. For every ending, a beginning. This rhythm, destruction and renewal, is not separate from us. It is within us. We too are born. We grow. We fade. And still, the story continues. So when you gaze upward, let it remind you that your questions matter. Your curiosity matters. You are not just a bystander in this cosmic play. You are a participant, a voice, a fragment of stardust that has somehow awakened enough to ask, why? That question alone is proof that the universe is not indifferent. For in us, it has grown a conscience. And maybe, just maybe, that is the greatest discovery of all. That the universe is not silent, it is not distant. It speaks through us as much as we speak about it. Each thought, each act of, imagination, each attempt to understand, it all becomes part of the ongoing dialogue between the infinite and the finite, between the cosmos and its children. So let this be your invitation. Keep searching, keep learning, keep wondering. Not because you will ever hold the final answer, but because the act of reaching is what makes you alive. To ask is to participate. To imagine is to belong. The night sky is waiting. The next revelation